All right. So, this is our last topic lecture this semester. This is it. Because on Friday we have exam review, and that's structural analysis. It's crazy, isn't it? We were just, computing reactions, it seems like yesterday.
Kind of were yesterday.
What's that?
We kind of were yesterday.
Yeah, I guess you were, yeah. One quick housekeeping item. I just want to show you something. So on the lecture last time, how we finished with this deflection formula, I had a slight typo here. I had an A there and it shouldn't have been, so I fixed that. And then I showed how we got from here to, from this formula to this one. And if you look, this formula matches what's in the guide. They just rewrote it in terms of X, but you can see where that came from. I just wanted to make sure that was clear. And then this integral, how I just sort of said, oh, there's the answer. I went ahead and evaluated it. And I did it in LaTeX just to make it look pretty, because why not? So yeah, just wanted to make sure you had that. Today what we're going to do is we're going to finish our final topic in the class, which is the concept of tributary area. We've already used tributary area a little bit with trusses. We're going to more formally discuss it, and we'll be able to actually connect your last homework assignment to the lecture today. So, and my bronchitis is still there, so forgive me if my voice is a little weird. Okay. All right. So let's talk about tributary area. Like I said last time, my goal for this week is the real world. And so what I mean by that is the bread and butter structural analyses that engineers are performing every day. And so Monday was about developing some of those quick and handy tools that engineers can use to assess routine situations. But what today is about is basically taking a building like this and turning it into the problems that we've been doing all semester. And it seems weird to do that at the end. You'd think you'd want to do that at the beginning, but I actually kind of prefer to do this at the end, because once we get to those familiar problems, suddenly they're incredibly easy to digest. Other than what I'm getting at is we have done oodles and oodles of structural analysis problems this semester, both in class, homework, on the exams. One of the things we haven't explicitly covered is how to take those principles and apply them in the real world, like explicitly. I mean, we did it a little bit with the project, and to be clear, I mean, if you were doing a truss analysis in the real world, that's how you would do it. But what we need to know now is to how to take those and distribute them essentially to a frame. How do we take a building element, a bridge element, and resolve it into the analytical models that we're familiar with? So the first thing that we do is we discuss structural loading in general. And I talked about this a little during the project discussion. But what we do as structural engineers is we typically specify our loads in terms of pressures or unit weights. So to use this building as an example, so the first thing that we might do is we might compute its dead load. So dead load for a building like this is largely going to be its self-weight. So let's say I'm trying to design the floor beams holding up not just this ceiling, but the floor above. Okay, so what do I got to account for? I got to account for the drop ceiling, the lights, the mechanical, electrical, plumbing, fireproofing, the structural frame itself, the metal formwork, the slab, etc. There's two really good places to find that information. The first is standardized specifications like ASCE 7 or other international building code, things like that. The other is the manufacturer. Like, for example, whoever manufactured these drop ceiling tiles is going to specify their weight in terms of a pound per square foot. So you as the, so if the architect has specified this is what we're using, the engineer could say, okay, there's the product number, here's the PSF, and that's what I can use for design, okay? And so manufacturers will do that for flooring or for ceiling, any really construction material. Sometimes we have calculations that may be a little bit more involved. So for example, with concrete, we might know concrete weighs 150 pounds per cubic foot, and so we need to multiply that times the thickness of the slab to get a PSF. It's like, as an example, if concrete weighs 150 pounds per cubic foot, and I have a 6-inch slab, 6 inches is half a foot, so that's 75 PSF, right? So you might have to do a little bit more of an involved calculation. And then you also got to be an engineer about it. If it's a 6-inch slab, do you actually design for 6 inches, or do you design for maybe 6 1/4 to account for a little bit of additional material or overpouring or whatnot? So that's something that happens on bridges. In fact, when you cast bridge decks, you actually purposefully overcast it a little bit for a couple of reasons. One, for maybe they'll grind it down later to set deck elevation, or two, wear and tear over the top. I mean, what happens in February to bridge decks in West Virginia? Some snow, and what goes over the bridge? Plows. And what do plows do to the bridge deck? They erode the surface of the deck, right? So there is a sacrificial wearing surface on the top of the deck to account for wear and tear. But traffic, snow plow. So that's one of the things you'll find that's kind of interesting from state to state, is that they'll have different specified thicknesses for sacrificial wearing surfaces dependent upon the conditions. So I couldn't tell you what they are in all 50 states, but I imagine that you'll find a trend that states that have more adverse winter climates might have higher degrees of sacrificial wearing surfaces because of the surface treatments that are done. So, and also, salts, chloride penetration, et cetera. I'm getting off topic, but I love talking about bridges. So, okay. Sorry. So, tributary area is something that we've dabbled with a little bit. It is the member that directly contribute, or is the area that directly contributes to the load on a given member. Okay. Tributary area is best defined as the area that's bounded by the lines halfway next to the adjacent beam and column. And what the method that I'm going to show you is going to work for 90% of all the building systems that you're going to be dealing with, as a structural engineer, and even bridge systems as well. There are a couple scenarios where what I'm showing you today isn't really going to work. So, for example, the slab systems that we're going to be considering today are what are going to be called one-way slabs. And so a one-way slab is one that is designed such that it only bends one way, right? So the idea is you've got beam, 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 and you have slabs that bend like that, okay? Most building systems utilize one-way slabs. Now, there are some instances where buildings will use two-way slabs. So the idea is that there really isn't like a line of beams. The idea is you have a grid of columns, the slab sits on top of that, and the slab actually bends this way and this way. So it sort of looks like almost like a square trampoline that's bending down like that. We call that a two-way slab. We use two-way slabs whenever we're really interested in making the floor system shallow. So I'll give you an example. You will find two-way flat slab construction all the time in high-rise buildings in Washington, D.C. Okay, and I'll tell you why. There is an ordinance in the city in Washington, D.C. that says that all buildings are limited to a certain height. They can't be taller than a certain something in Washington, D.C. What do you think that is?
The White House? Or the Capitol?
No. What's the really tall thing in D.C.?
Oh, the monument?
The monument. The monument. You can't have buildings taller than the monument, right? That's a city ordinance. But you're a developer. You're a real estate developer, right? The more square footage in your building, and given the fact that you rent out that space at a cost per square foot, the more square footage, the more money you make, right? So you want as much square footage as possible, right? So it's in your best interest if you only have this much footprint on the ground to make the building, oh, my bad. You only have this much footprint on the ground, it is advantageous to you to get as many stories in the building. So if a normal one-way slab just to make it simple, let's say a normal one-way slab system is only going to be 18 inches deep. A two-way slab might be 12 inches deep. You think, well, that's only 6 inches. Well, add that up over 30 stories, and you get another story in the building. Another story means a whole nother floor. A whole nother floor means a whole nother 1,000 square foot that you can rent, get more money, right? So two-way slabs you'll see in that type of construction all the time. The other place you'll see two-way slabs is whenever you have a really heavy load on the floor. Drinko has some two-way slabs because the second and third floor has book stacks. Book stacks are really heavily loaded. They have a waffle slab system in there that acts as a two-way slab. So again, I digress. I can't help it. Okay. Now we've looked at tributary area for a truss, but we haven't looked at it for a floor system. Okay. So I have a really, really simple floor plan here on the screen. Okay. Now what we're looking at is the frame of a building as if we're in a helicopter looking down. Okay. So the black squares here, these are the columns that are sticking up out of the ground. Okay. Now we use sort of a hip bone connected to the leg bone type of terminology. So first off, we have the columns, and then we have the term beams and girders. Okay. Now the way that I like to describe it is that these are the beams. The beams frame into the girders, then the girders go to the column. Column goes to the ground. Okay. So if we're looking at tributary area, let's take a given beam like, I don't know, let's take this one. The tributary area for that beam, halfway over to the next one, halfway over to the next one. That's the tributary area. That's what that beam is responsible for. Okay? So what we'll do is we'll take the pressure load applied on that beam, multiply it by the tributary width, and turn that into this. Now that's familiar. Didn't y'all do this problem yesterday? Or at 9 o'clock this morning? Oh, well, I'm sorry. Acting like I don't know things about stuff. I know things. So, all right, if we're only considering gravity loads, making sure we're paying attention, what can you tell me about these edge beams versus these interior beams?
They're responsible for less load.
They're responsible for less load. So if I'm a designer, what does that mean?
It can be a smaller member.
It can be a smaller section. Exactly right. That's exactly right. Okay. Now, that is only under the consideration of a pressure load. In practice, sometimes that doesn't always happen for a couple of reasons. One, there's also the wall that goes around the building. So if the edge beams are having to support the wall, maybe they end up actually being bigger because they have to support the wall curtain, right? And by the wall curtain, like in this building, I'm talking about the bricks that are outside the building. I mean, you have a 6-inch thick brick facade hanging over the side of the building that has to be held up by something, right? So that's something that has to be supported by these elements on the edge. The other is you're going to have some component in the building that's resisting lateral loads, like earthquakes or wind. It's not like wind's anything you got to worry about, right? It's been a windy day today.
You ripped the doors off my building last night.
Yeah, it's been a heck of a windy day today. And so there's particular elements normally on the, at least around here, you'll usually find them on the exterior facade of the building. Those elements are going to be pretty big because they have to resist those lateral forces. Okay, now, if we're talking about the girders have a much wider tributary area. If we're talking about this girder, halfway over, that's going to be its tributary area. Now, here's the thing about the girders, though. The girders don't always experience just a big distributed load. I mean, let's look at this beam right here. Okay, here's the beam. What are the reactions? Did you all figure this out? WL over 2, right? Where do those reactions go? to the girder, right? Because here's the beam, right? So we've got a beam and it's connected to a girder on either end. So if I'm looking at this girder right here, 1, 2, 3, 4, really the girder's seeing something like this. 4 point loads on the girder. And those point loads correspond to the reactions, right? Now what's interesting is that for interior girders, these point loads are, okay. For the interior girders, these point loads are 2 reactions, because if we're talking about, let's say, this girder, there's a reaction from this beam, and there's a reaction from this beam, and from this beam. So 2 reactions for each one of these. For the exterior girders, just 1. Does that make sense? And the columns, so if we're looking at the columns, we actually have a couple different ways of looking at that, and statically they're equivalent. So if we're looking at, let's say, B is going to be, you know, like that tributary area. Sorry, B1. So we can just take pressure times area. But I'll show you how that works here in a bit. Does that make sense? Okay. So again, I think I've shown you this before, but this is a picture I took of the parking garage in 3rd Avenue, or on 3rd Avenue. So for example, if I'm looking at, let's say, that beam, that's its tributary width, right? So take the pressure load of the floor acting above it, multiply it by the width, and I can turn that into a beam like this with a distributed load. Now, that beam's going to have reactions, right? Those reactions are going to act as point loads onto this edge girder here on the end. Does that make sense? So now what we can do is take, maybe the self weight of the beam and treat it as a uniform distributed load, and then add to that the effect of these point loads. Get a shear moment, use that size of this beam. You can see this beam's going to have a little bit more on it. It's a little bit deeper. So got a lot more moment on it. Does that make sense? Yes.
So you're saying reaction A would be on the end of the beam goes to the outside would be the same as downward force.
Yes. Yes.
And you had it for every one of them, whole length of the field.
Yes. Yeah, because what's going on is this. So like, here's the beam, right? And it's, there's the reaction force, right? And there's the spandrel girder that it's sitting on. So the spandrel girder is seeing that downward effect. Does that make sense? So, that's a good question. Anybody else? Is good stuff. Let's do a floor plan. And this is the floor plan that we're going to do. So let me open up the notebook here. Make this a little bigger. I'm actually going to copy and paste this a few times. Just so I have it a few times. Okay, so we've got a floor system that is subjected to a 20 pound per square foot load. Okay, and I want you to think about that in your head. Okay, we're talking about, a patch this big. It's got 20 pounds on it. I mean, like that big. The amount of force generated from that load is surprising. We're going to see columns with thousands and thousands of pounds on it just from that. It's kind of crazy. Now what we're going to do is we're going to sketch the tributary area for an interior beam, for a particular girder, and for a particular column. And for these elements, we're going to determine a couple of things. We're going to determine the distributed load on a typical interior beam, and we'll analyze that beam while we're at it. We're going to determine the concentrated loads on girder C2D2. I should have named that one grid R.
I got it.
You got it. And then, I'm a dork, I know. And then, one of the axial columns, or one of the axial loads on one of the columns, on column B2. Okay? Now let me scroll down here. So here's my floor plan. So we'll do the interior beam first. And by interior beam, what I'm basically saying is any one of these elements in the middle, okay? I'm not talking about the ones on the A line or the ones on the D line, okay? By the way, and I don't know if you've seen this, but this is very common framing plan notation for a building, that what you'll do is you'll label one direction with letters and then one direction with numbers. Sometimes it's flipped, but this is usually how I see it. And so that way, if we're talking about column C3, we know what we're talking about, okay? And sometimes framing plans can get a little wonky because buildings can get a little wonky. So sometimes you might see A, B, BB, BC, C, you'll see some odd configurations if there are some interruptions in the framing plan. So I kept it pretty simple for today. So we'll pick a typical interior beam. Let's just pick, I don't know, this one. And the tributary width, or the tributary area, going to be halfway over. So this is the tributary area. Somebody tell me what that tributary width is. What is that tributary width? So this is 10 feet between the beams. So we go halfway over. What is that?
10 feet.
10 feet. So for the beams, we have the tributary width of 10 feet. How long are they? 30 feet. Okay. All right. So, okay. And forgive my artwork here. Okay. Don't forget, we're applying a pressure load of 20 psi. Okay. So here's what the beams look like. Okay. And again, forgive my artwork. I'll do my best. All right. That's about the best you're going to get. So these are the floor beams in 3D. How'd I do?
Pretty good.
Did I do okay? Okay.
Had me for the last one.
Okay. I haven't done it yet. I'm going to give you the professor look. All right. I love my job. Okay. Let's put some dimension on this to make sure that we're referencing this to the framing plan. So this is 10 feet, right? Now, the floor system is seeing a pressure load, right? It's seeing a 20 PSF pressure load across the entire system of the floor, okay? Now, what's happening is, so if I'm focusing on this middle beam is responsible for halfway over, halfway over, that's what this beam is responsible for, right? I got a little wavy on there. But that's the tributary width for that beam, okay? So this is the tributary width. And in this case, this is the span length, okay? Now, what I ultimately want to do is I want to turn this into just looking at a beam, okay? I just want to look at a single beam, okay? So keep in mind that what's going on in this area, let me draw it like this. What's going on in this area is seeing a pressure load act on top of it, right? It's seeing, this pressure of 20 PSF act on top of the beam. Now what I'm going to do is distribute that to this beam so that the beam is seeing just a distributed load. Now how am I going to do that? I have a pressure load of 20 PSF and it is applied over a width of 10 feet. So I have 20 PSF applied over a width of 10 feet. How much load per foot is that beam seeing? 20 pounds per square foot over a width of 10 feet. How much width or how much load per foot? 200 pounds. That would be the entire load, right? Right. So the distributed load is the pressure load times the tributary width. So here's our analytical model. Bless you. Oh, that was bad. That's the analytical model for a beam. And that I can handle, right? Because I derived equations to handle any beam that looks like that, right? Well, I didn't, you did. For example, what is the reaction? What is the vertical reaction? WL over 2? Right. No, 3,000, yeah. Right? 3 kip reaction. What about M max? What did your homework tell you? WL squared over 8? That is a very handy formula next semester. And in concrete design as well. Somebody tell me with your Casio FX115 ES Plus or similar scientific calculator what you get for that. Excuse me. Oh, no, I got the square. What do we got? It's a big number.
20,500.
Second. Now, what are the units? No.
Foot. Pound foot.
There you go. .5 foot kips. Pretty crazy, right? So now those aids are starting to be pretty useful. So now I'm an engineer. I just need to select a beam that can hold up that much load. Okay? Let me. Oh. All right. Let me stop for a second. See if this made sense. Anybody have any questions about this? Sound good? All right. Now let's have some fun with this. Okay. Now let's look at. Let's look at interior girder C2D2, okay? Now, the problem's asking us to find the concentrated loads on the girder. We'll probably do a little bit more than that, but let's just see what happens. So, here's the frame. So, we're talking about girder C2D2. That's that girder, right? So, first off, drawing the tributary area, halfway over, halfway over. So there's our tributary area, but instead of distributing that load as a distributed load, bless you. See, I could do the same thing I just did. I could just say tributary width times pressure load and put a distributed load on that. I'm going to use the hip bone connected to the leg bone analogy. And I'm going to say I've got interior beams framing in to this point, this point, this point, and this point. So instead, this girder's what, 50 foot long? We have 4 point loads applied there. Now some of you might be thinking, what about this beam or this beam? Well, I'm just going to assume that goes right to the column. You'll see why here in a second. But let's put some dimensions on this. So we know that. How much are these loads? How much is each one? Well, how much were the reactions for the beams? 3 kips. So is this 3, 3, 3, and 3? It's 6 because there's a beam here and there's a beam there. That point right there has 2 beams. So this is 6 kips. 6 kips. So what you can say is you can say so what are the reactions?
Well,
12, right? 24 on top, it's all symmetric. 12. 12. And if we wanted, we could get a little crazy. We could say, all right, There's our shear diagram, and go from there, right? I'm not going to do any more. But you see what I mean, right? Notice how it's actually a pretty easy shear diagram. It's all rectangles, right? So 120, 60, 0, negative 60, negative 120, it all balances. It's all linear. We actually have a constant moment region in the middle. So really cool stuff. Let me stop for a sec. Does this make sense? So what if we did that girder? What if we did B4C4? What would happen? It'd be 3 kips, not 6, because it's one on the edge. It's only seeing half of it, right? Make sense? Okay. All right. I love this part. This is one of my favorite parts. Now we're going to do column B2. Okay? Now in order to do column B2, I want to recall this, and I want to recall that. So we have a pressure of 20 pounds per square foot, but I also want to recall that the beam reaction was 3 kips, the girder reaction was 12 kips. Okay? Now, this is column B2. So our tributary area, halfway over to the next column, halfway over to the next column, halfway over to the next column, halfway over to the next column. That is the direct component that column is responsible for. What is the tributary area of that column? What is this dimension right here? Come on. That's 50. What is this dimension? So everybody okay with that? So one way that you can determine the load on B2 is to take the pressure, 1,500 square feet, and what do we get for that? 30,000 pounds? Which what that means is, you know, here's the column sticking out of the ground, here's the support on the ground, and we have a column that's seeing 30 kips on it. But another way, is to look at that column in the framing plan. How many beams are framing into that column? 1, 2. How many girders? 1, 2. So another way is to say Statics doesn't lie. But in the end, whether you use a pressure approach or you distribute the reactions, you'll get the same answer. It's kind of crazy, isn't it? It's a check on the whole thing. I love that part. But notice, okay, I want to be clear. That 30,000 pounds on that column is only from one story, okay? What if we had a 4-story building, okay? So let me show you what that would look like, okay? All right, so let's say we had a 4-story building, and let's just assume for simplicity that all the floors are the same. They're all equally loaded. So let's say here's your column, here's your ground, and like just to keep this simple, like let's say here's your roof, so that's a story. That's a story. That's